Everyone. Welcome back to another lesson in MCV4U. Today we'll be looking at the force as a vector. So a force is defined as a push or pull on an object, a push or pull on an object that causes it to accelerate. It acts in a specific direction and is a vector, which means that it has both direction and magnitude. The unit of force is Newton, which we represent using N, named after the famous physicist Sir Isaac Newton. And 1 Newton is the amount of force required to give a 1 kilogram mass an acceleration of 1 meters per second squared. Or in other words, 1 Newton is equal to 1 kilogram times 1 meter per second squared. And according to Newton's second law, the net force of an object is the product of the object's mass, m, in kilograms, and the acceleration, meters per second squared. So here, force again is equal to mass times acceleration, where again, F is the force in newtons, m is the mass in kilograms, and a is the acceleration in meters per second squared. And a note here, when we look at the mass is a scalar quantity because it again has no direction. Again, Newton also famously discovered that on Earth, acceleration due to gravity is constant, and so on Earth, a free-falling object will have an acceleration of 9.8 meters per second squared in the downwards direction. When two or more forces again act on an object, the net effect of the forces is the resultant vector. So again, when two or more forces act on an object, the net effect of the forces is the resultant vector. Okay, so this example says, again, two forces are applied to a boat. The first force is 1,000 newtons in a 30 degrees north of east direction, and the second force, F2, is equal to 2,000 newtons in an easterly direction. Again, to determine the resultant force. So here, again, if we draw a diagram, label it north, east, south, and west. So the first thing we know here is we have our first force. Again, there's 1,000 newtons. And again, it's 30 degrees north of east. We see that we have our second force that's pulling the boat. That is 2,000 newtons. And that's just going in easterly direction. Here, again, we can move that 1,000 newtons or redraw it here. And we'll see that our resultant vector will be here as well. So here's our resultant vector, which is r. So here we see that if this is 30 degrees, then again, this entire angle would be equal to 60 degrees, and therefore this angle here, take 180 minus 60, will give us 120 degrees. And so here, if we're trying to find again our magnitude, and we can use cosine law. So here we have r squared is equal to 1,000 squared plus 2,000 squared minus 2 times 1,000 times 2,000 cos 120. So here we get an R value when we calculate it as 2,645.8 newtons. So there we found the magnitude again, but we're trying to find the vector, so we need to find here the direction. Now here again, we're trying to find theta. So here we sine law, so sine theta over 1,000 is equal to sine 120 over, again, the value that we just found, which is 2,645.8. Here, we'll get an answer of theta is equal to 19 degrees. Again, in terms of our direction, we'll take our 90 degrees subtracted by 19 degrees, which will give us 71 degrees. And so here, therefore, our resultant vector is 2,645.8 newtons, 71 degrees north of east. So we look at equilibrium vectors. So equilibrium vector is a vector that balances other vectors. It is equal in magnitude, but opposite in direction to the resultant vector. So if the equilibrium is added to the given system of vectors, the sum of all vectors, including the equilibrium, is 0. So here it says a clown with a mass 80 kilograms is shot out of cannon with a horizontal force of 2,000 newtons. Three things we're determining here. So it says determine the gravitational force of on the clown towards the ground, find the magnitude and direction of the resultant force on the clown, and then find the magnitude and direction of the equilibrium force on the clown. So here, if we start, again, we know that again, force is equal to mass times acceleration. And again, we know that the gravitational force is 9.8 meters per second squared down, which represents gravity. And here we know that the mass of the clown is 80 kilograms. So we'll multiply that by 9.8, which the force we'll get is 784 newtons down. So here, again, if we draw this in terms of our diagram, see that clown is massive. It's shot out of the cannon with a horizontal force of, again, 2,000 newtons. Again, here we just calculated, again, that the gravitational force is 784 newtons. Here, and we can draw the resultant vector. And we have our angle or theta here. And here, again, if our resultant vector is going this way, then again, we're going to find the magnitude and direction of the equilibrium force on the ground. Just going, again, the magnitude is the same, but it is in the opposite direction. And we'll represent that as vector E. So here, if we found the resultant force, that's equal to square root of 2,000 squared plus 784 squared. And so here, R is equal to 2,148 newtons. So here we're going to find, again, our angle here. So we're going to use, again, our trigonometric ratios. So here, our primary trigonometric ratio. So here we see that tan theta is equal to 784 over 2000. So here we see that theta is equal to 21 degrees. So therefore, we see that the resultant vector is 2,148 newtons, and it is 21 degrees clockwise of the horizontal. Okay. And so here, then we see that the resultant is 21 degrees clockwise, again, of the horizontal. And so therefore, the equilibrium force will be same magnitude. However, again, it is the opposite direction. So if it is 21 degrees clockwise from the horizontal for the resultant vector, the equilibrium force will be 159 degrees counterclockwise of the horizontal. Okay, so here we see that the traffic light at an intersection is hanging from two wires attached to a horizontal bar. One traffic wire makes an angle of 10 degrees with the bar, and the other one makes an angle of 20 degrees. Again, with the bar, the traffic light weighs 250 kilograms. What are the tensions on the wire? Okay, and so just notice here again that since the light is not moving, the sum of the forces, again, must be zero. We say that the system is here at equilibrium. So here, again, we have our picture here, and here we know that our force is equal to our mass times acceleration. Here we know that the traffic light weighs 250 kilograms. And here we have our gravity at 9.8 meters per second squared. So here our force, that's our equilibrium force, is 2,450 newtons. So here we see that the equilibrium force is also 2,450 newtons. Okay, so here, if we draw the diagram, and here again we have one wire, again that makes an angle of 10 degrees. So write that here, so 10 degrees. Again, which means that here we will have 80 degrees because that creates 90 degrees, and that's going to be our first tension. And then here, the other wire makes an angle of 20 degrees, which means we see that this would be 70 degrees. And this angle would have to be 30 degrees because, again, 180 minus 80 minus 70 would give us this 30 degrees. And here, this would be the tension here. Here, we calculate it again. The force that's acting upon this is 2,450 newtons. So here we'll find the tension of tension 1 and tension 2, and we'll calculate this using sine law. And so here we have sine 30 over 2,450 is equal to sine 70 over the first tension 1. And so tension 1 is equal to 2,450 sine 70 over sine 30. And so tension 1 is equal to 4,600 4,604.5 newtons. We'll do the same thing to calculate for tension 2. So here's sine 30 over 2,450 is equal to sine 80 over tension 2. Tension 2 is equal to 2,450 sine 80 over sine 30. So tension 2 is equal to 4,825.6 newtons. And so therefore here we see that tension 1 is 4,604.5 newtons, and tension 2 is 4,825.6 newtons. Okay, so let's keep looking at this example here. So again, it says, which of the following sets of forces could produce equilibrium? And so here, again, for equilibrium to exist, three vectors must be able to close off to make a triangle. So given a triangle with sides A, B, and C, where C is the longest side, A plus B must be greater than equal to create equilibrium. And so here, if we look, we have 15, again, newtons, that's the longest side. Again, so here 10 plus 8, 10 newtons and 8 newtons, if we add those up. So 10 newtons plus 8 newtons, again, would be greater than 15 newtons. Again, so here, this produces equilibrium. Here we have our longest side is 13, so 7 newtons plus 5 newtons. 7 newtons plus 5 newtons is less than 13 newtons, so that does not produce equilibrium. And then here we have 11 newtons being the longest side. So here, if we add 5 newtons plus 6 newtons, that is equal to 11, which again does produce equilibrium. And so here, if we look at the horizontal and vertical components, so again, a single force can be decomposed into the sum of two components. Generally, we wish for these components, again, to be perpendicular and express the original vectors in terms of its horizontal and vertical components. So here, if we look at our diagram, again, here if we have the magnitude of the vector f of x, that is equal to the magnitude of the resultant vector f cos theta. If we look at the magnitude of vector fy, that's equal to the magnitude of the resultant vector f sine theta. So here, if we look at this example, it says a tractor, again, is towing a log using a cable inclined at an angle of 15 degrees to the horizontal. So again, here we draw a diagram. So again, tractor's towing a log using cable inclined at 15 degrees to the horizontal. And if the tension in the cable is 1,470 newtons, and what is the horizontal force moving along the log? So here, our horizontal force, the vector f of x. So here, again, the magnitude again of the vector f x is equal to the magnitude of force times cos theta. And so that's equal to 1,470 times cos 15, which is equal to 1,419.9 newtons. So therefore, the horizontal force is 1,419.9 newtons.